So in the second video, we're going to continue to talk about the definite integrals and that definite integral notation, and we're just going to do some general properties in the rest of this section here. So a few rules for working with definite integrals. So make sure you take good notes on these because we're going to use these rules quite a bit for the rest of this section. So if you have the integral of a function from a to b, sometimes it's helpful to reverse it and write it as the integral from b to a, and then just put a negative sign in front of it. So sometimes that'll help you to evaluate certain problems, and that's what we're talking about. We'll see some examples with this in a few minutes. The integral of the function from a to a is 0, and that should make sense to you because if you don't go anywhere, if the upper and lower limits are the same, there's no area underneath that curve to look at, and so the limit would, or the integral would be 0. The constant multiple rule that we used earlier in the chapter for antiderivatives, that can be used again. So if I have a constant function and it's helpful to work out the area under the curve by moving that constant to the front, we can still do that. Likewise, the sum and difference formulas still work. So if we're adding and subtracting two functions with a definite integral, we can still move those, or we can still separate them into two different integrals if that helps. This integral rule is actually quite important. It's kind of like the transitive property. It says if I have the integral of the function from a to b and I add that to the function, the integral of the function from b to c, that can be combined as the integral of the function from a to c. And so if you look at a picture, this should kind of make sense. If the area under the curve from a to b is added to the area under the curve from b to c, that's equivalent to the area under the curve from a to c. So sometimes it helps to break up integrals this way. If f is integral and non-negative, so in other words, if the function you're looking at is non-negative, everything's above the x-axis, then the integral from a to b is going to be greater than or equal to 0. It's going to be positive, and that's going to that should be very intuitive, I think. If what you're looking at is above the x-axis, when you integrate, your integral is going to also be positive. If the function, if f of x is less than or equal to g of x for all x in the interval a to b that you're working with, then the integral from a to b will also be less than or equal to the integral of g of x from a to b. So let me say that again. The integral from a to b of f of x, because that's below g of x, will also be less than the integral of g of x from a to b. All right, so let's practice figuring this out. Now here's the good news. As we get further into the next couple of sections, we're not going to have to keep using that limit and those summations every time. So for the rest of this section, unless they tell you to use a limit and to use those summations, let's try figuring out these integrals in some other way. And sometimes using geometry and drawing a picture can help us do that. So this is asking us for the integral of the function 4 from 1 to 3. So if you think about what that looks like, the graph of just y equals 4, that's a constant horizontal line. So what they're essentially asking us for is the area under this curve. This is a non-negative function, so the area under this curve from x equals 1 to x equals 3. Well, if you notice, this is a rectangle, so we can figure this out just using geometry. So the length of the rectangle would be 2, the height of the rectangle would be 4, so the area would be 8. So that would represent the integral of this function from 1 to 3. Let's try another one. They want us to work with the integral of the function x plus 2 from 0 to 3. So let's make a sketch of this. And so we have a line with a slope of 1 and a y-intercept of 2. And so if we're going from 0 to 3, what I want you to observe is that we have a trapezoid here. Because it's a regular figure, we can go ahead and find the area using geometry. And you may not remember the area of a trapezoid. That's okay. The formula for it, let me show it to you. It's 1/2 base 1 plus base 2 times the height. So base 1 and base 2 are the two sides that are parallel. So keep that in mind. So the two sides that are parallel have a length of 2 on this side and a length of 5 on this side. The height is the distance between them. So we have 1/2 times 2 plus 5, those are your bases, times the height, the distance between them, which is 3. And that simplifies to 21 over 2. So that is the value of that integral. We could go through and still do the limit summation process. We'd get the same result. But what the point here is, if you can do it in some other way, in this case using traditional geometry formulas, because these create regular figures, go ahead and do that. Let's try another one. So we're looking for the integral of the function square root of 4 minus x squared from -2 to 2. You may or may not recognize this, and that's okay if you don't. This is a semicircle centered at the origin with a radius of 2. So what we're looking for here is how to find the area of a semicircle. So remember, we did one not too long ago where we looked at a Norman window and we talked about the area of the semicircle. Remember, it was pi r squared divided by 2. So the radius, of course, is 2, so it's pi times the radius squared divided by 2, which simplifies to 2 pi. So the integral of this function from -2 to 2 is equivalent to 2 pi. And what you notice, this is all above the x-axis, and so we're getting a positive quantity. Okay, how about this one? We're looking at the integral of the function sine x from pi to pi. And of course, that's just going to be 0, right? That was one of our properties from earlier. If you don't go anywhere, your lower limit and upper limit are the same. Your integral is just 0. Okay, how about this one? We're looking for the integral of the function x plus 2 from 3 to 0. Now, I put this one in here because we just worked with the integral of the same function from 0 to 3. Let me back up a couple slides here. This example, remember we did this example? Same function, x plus 2, but we went from 0 to 3. So remember, one of the properties you wrote down earlier said that if you reverse the limits of integration, you can negate the integral and have an equivalent value. So this is equivalent to the integral from 0 to 3 negative. So in other words, the negative of the integral from 0 to 3 of the same function. So remember that integral from 0 to 3 was 21 over 2. We're just going to negate it. So that combines the property we talked about earlier with the value we got in the last example for the area under that curve from 0 to 3. Okay, how about this one? We want the integral of the function negative x squared plus 4x minus 3 from 1 to 3. And they gave you in this function a little bit of information. They told you the integral of the function x squared from 1 to 3 is 26 thirds. You don't have to know that yet. We'll have a process later on to help us figure that out. But for now, take their word for it. They're giving you that information. They're also giving you the information that the integral from 1 to 3 of x is just 4, and the integral of just dx, which is really an implied 1, from 1 to 3 is 2. So the idea here is they want you to use integral properties to separate this out, simplify it, and use these values for these respective integrals that they're giving you. So the first part of this can be written as the negative of the integral x squared from 1 to 3 plus 4 times the integral of x from 1 to 3. All I'm doing here is I'm pulling out these constant multiples to the front because that's a property of integrals. And then the last one, same thing. 3 times 1, of course, pull the 3 to the front. Now look what you have. You have the integral of x squared from 1 to 3. That's given to you right here. So you're going to substitute 26 thirds. Same thing with the next integral. The integral of x from 1 to 3, they told you was 4. So you're going to substitute that in down here. And then the last one, that integral value is 2, so you're going to substitute that in. So we have negative 26 thirds plus 4 times 4 minus 3 times 2, which simplifies to 4 thirds.